This is problem 22 in chapter 7, and this is an interesting problem because there's actually two ways to solve it, and mercifully they come up with the same answer. The first way we'll consider only energy. In this example, there is a train that has a mass of 5 times 10 to the 5th kilograms, and it's moving at 0.5 meters per second, and it's going to run into a spring which is initially at its rest position. After colliding with the spring, the train comes to a stop and the spring is compressed to a distance of 0.4 meters. The challenge for us is to find the spring constant K. So, from an energy point of view, what if we consider the system to be both the train and the spring? Okay? If the energy is this train, if the system is the energy in the train and the spring, let's take a look at keeping track of energy in that system. And I'm going to take the time to write this out. I know it drives you all nuts, but it helps me keep track of all the energy and the work and everything that's going on. Now, in this example, we start off having kinetic energy of the train. So that would be 1/2 mv squared. There's no potential energy. The spring is at its rest position, and also it's on level ground, so the potential energy is 0. There's no friction talked about in this problem. And what about the external work? Since the spring is part of the system, the forces that it creates, they do work, that's true, but that's internal work, and so we can keep track of it with energy. So there's actually no external forces acting on the system, so there's no external work. After the train has come to stop, it obviously has no potential energy, no kinetic energy, but the spring is now compressed, so it has potential energy due to the spring being compressed. It wants to expand, and that's 1/2 kx squared. So in this problem, the initial kinetic energy will equal the final potential energy, not gravitational, but spring. Solving for this, the initial kinetic energy is 1/2 times 5 times 10 to the 5 kilograms times 0.5 meters per second squared. So this equals a number of 62,500 joules. That's my initial kinetic energy. So that has to equal 1/2 kx squared, and the x is 0.4 meters squared. When we solve this, we get K equals a very large number, which is 781,000, and the units are newtons per meter, meaning for every meter that the spring is compressed, it will generate 781,000 newtons of force. Okay. This is a fairly easy solution, and it's a solution that makes sense and corresponds to when we treat the system as both the spring and the train together. But alternatively, and equally valid, I could treat the system as just the train. If that's true, then I have the same initial kinetic energy. I have no potential energy, I have no non-conservative work of friction or anything, but I do have external work. The external work is the spring pushing on the train. If the system is the train, then the spring is creating an external force on that and working to remove the energy from the train. The train comes to a stop, and even though the spring is sprung, it's not part of the potential energy of the system. The system is the train. It's still on level ground. There's no gravitational potential energy change. The fact that the spring is compressed just means that it's pushing on the train at the end of this situation. But it's done its work by pushing with a force that's changing on the train over a distance of 0.4 meters. Okay, so now we know that we have initial kinetic energy of 62,500 joules. We also know that external work is the force times the distance. Okay, and the distance is 0.4 meters. Now, the force of a spring is kx. And we want to make sure that we're taking the average force. What am I talking about here? When the spring is at its rest position, it creates no force. As it's compressed, the force increases because F equals kx. At its maximum compression, it creates the maximum force. At 0.4 meters, that would be its biggest force. But its average force is half of that. If I plot this, the force, as I'm squeezing compressing the spring, its force increases to a maximum value at 0.4 meters. But the average force, which is what I want to take over the whole period of time, is equal to the force at 0.2 meters. So this d here is not 0.4 meters, it's 0.2 meters. Okay? And x and d are the same. X is the compression of the spring, d is the distance over which it acts. Sorry, I got that backwards. X is the average compression of the spring, 0.2 meters. D is the distance over which the average force works, 0.4 meters. So if we write this out, 62,500 joules equals the spring constant, which is what we're trying to find, times the distance where the average force is, times the total distance that the spring acts. Okay. When you solve for k in this situation, you still get 781,000 newtons per meter. So it's a radically different problem depending on whether we treat the spring as part of the system or the spring as an external force. Get the same answers, need to keep track of it the same way.